Hello everyone, welcome to the MATH2019/2018 revision seminar. This is part 2. Good to see some familiar faces. If you're tuning in online, welcome. So I just want to preface with, if you guys have any questions at all in the middle of the seminar, if there's anything you're confused about or you want us to clarify, please raise your hand, ask a question, feel free. Yeah, we're more than happy to take questions if you guys get confused. So, I suppose we'll get started now. So, today we're starting off with vector calculus. All right, so in vector calculus, really one of the most fundamental things we look at is curves. And right here is an example of a curve. And typically we parameterize it as a function of time. We parameterize the x, y, and z coordinates in terms of time. And it traces out some path as time goes along. So we say that as time varies from 0 to 1, we get this curve being traced out. So nothing too crazy. Now, I guess the next really fundamental thing in vector calculus is the idea of vector fields, right? And what it does is it takes a point as an input and it associates a vector to it. So we have every point in three-dimensional space here has a given vector. So we can think of this as like a force field. So if you put drop a particle in there, it will follow around wherever those vectors push them. So some pretty standard stuff. Now, the next thing we have is line integrals, and it's now what we actually do with these vector fields that matter, right? So we take that curve, C, that we looked at just before, and if we parameterize it over some interval, right, typically it might be a to b, usually 0 to 1 is a good parameterization. We define the line integral to be the integral of this vector field with respect to the position vector r. And we can, just with a bit of algebra, like if we compute the dot product and express, the position vector r in terms of x, y, z, and work out all that stuff, we end up with this nice expression here. We get that we can take it out of this weird abstract form with the c here, and we can put it into something that we can actually compute. So this is just a formula that's given to us. It's really simple. Parameterize the curve, plug the numbers in, and we're good to go. So, and the really important thing is that this integral here, this integral of the vector field with respect to r over some parametric curve c, it tells us the work done. And I guess the way we can think of this, from classical mechanics, a lot of you guys would have taken in like Phys 1a, we know that work is the integral of force with respect to x, or with respect to position. So we draw this like vector calculus, I don't know, this is like the analogous version in vector calculus. It's now this, the force field with respect to our position again. So it's sort of the same thing, similar, just in different contexts. So here's an example. We've got a force field, F, given by this expression here, and we're told that the path C is a straight line, very nice, from this point to this point in R3. So we want to find a parametric representation for the path C and hence evaluate the work being done. So in other words, what's the parametric equation for the curve C? Hence do the line integral. That's all it's really asking. And we can express this integral like this. That's just using this expression here. No, sorry, it's not that one. It's just this one here. So we can rewrite our integral into something that's a bit simpler to look at. Now, the first step is we parameterize the curve. Well, how do we do that? Right? We're talking about all this parameterization. How do we actually go about doing this? So here we have straight line parameterization. So if we have a straight line that goes from point A to point B, we can use this formula to parameterize it, where A is the first point, B is the second point. Alternatively, the formula that I much prefer to use is this one here. I just find it's a lot easier. So, and this is, of course, in our example, A is the point, let's have a look. A is 431. Oh, being left-handed is not helping me. 431. B is equal to, our point B is 635. So now it's just a matter of plugging this into the formula. So we can say that the point A we just represent with the vector 4, 3, 1, which is this point here. And then the point B, or I guess this vector here, the way that we get this is this is the vector from A to B. So we think, oh, how do I get from the x-coordinate of A to the x-coordinate of B? Okay, well, I'm going from 4 to 6. Okay, so I move across 2 units in the positive direction. Okay, well, if I'm getting from 3 to 3, I'm moving across 0 units. So that's why this term here is a 0. And then if I'm moving from 1 to 5, I move across 4 units. So this is why this is a 4 here. So that's where we get our parametric representation of our curve C. So we can then say, just by vector addition, because these are both vectors, it's a bit wonky, but if this equals x, y, z, then x is just going to be the top row, so that's where we get the 4 plus 2t. Y is going to be just 3, and then z is going to be the 1 plus 4t, which is that bottom row. And then simply just by differentiating all of these with respect to time, we end up with this. So what we can then do is, looking back at our integral, we can replace the dx's here, the dy and the dz, with dt. So we're integrating all with respect to one common variable, which is very nice. So now it's actually in a form that we can integrate. So here we go again, this formula. So we're just plugging it in to this expression. And so I'll write the original curve. The original curve that we had was, so 2yi, x, y, z, 3e to the x plus y. So what we're doing is that parameterization that we had, x of t, y of t, z of t, we just plug that in. So when we see a y here, we plug in y of t. Where we see x, y, z, we plug x, y, z of t, respectively. And then in this e to the x thing, we plug x of t and y of t in. So that's what it means by like f1 of c of t. So we plug in whatever the respective x, y, z parameterizations are. Okay, so doing that, right? It's nothing crazy. I don't think, for the sake of time, I'm not going to sit here and plug everything manually and compute it. But we end up plugging in into our first term to get that. Our 2y, this is our 2y, which is the y's here. And then this middle term it's going to be an x, y, z, right? Which is going to be the product of all of these. Yucky. But dy is just 0, so the whole thing goes to 0. Sweet. And then our last term, the x plus z, we end up getting this term here, which simplifies to a very nice integral of the form 12 plus 12e to the 2t plus 7, which we can integrate very easily, and then we just plug in our bounds 0 to 1. So that's how you do simple line integral. It's just a matter of parameterizing c, plugging x, y, z of t into your function f, and then integrating with respect to t. Plain and simple. So now the next thing that we learn with vector fields is this idea of divergence and curl. And they have, there's geometric significance to what divergence and curl actually means. So divergence is if I've got a point here, and I've got vectors shooting out of here, we say that there's a positive divergence. It's diverging away from the point. And then, obviously, if it goes into the point, it's negative. And then curl just means how much it curls around a specific point. That's a really wonky arrow, my goodness. Like this, so a bit like a whirlpool. And we have equations for these, which is given by this. And again, we see this nabla vector operator appear. And oftentimes it's helpful to think of nabla as a vector, like partial on partial x, partial on partial y, partial on partial z, because then we can do just dot products and cross products. We can just think of it as vector operations, and it works out very nicely. So these are our two equations. We're probably very familiar with these. Now, we have a very special kind of vector field, and that's when the curl is 0. So it means it doesn't rotate or curl around any specific point. And And we express this as a gradient function. So the gradient function, that just means it's some phi of x, y, z. And then we apply nabla to it to turn it into a vector and differentiate our components. We get a corresponding vector field. We call these conservative fields. They're also referred to as irrotational. There's like a million different names for it, but conservative is like the overarching name. That's normally what we call it, and it just means that it doesn't rotate. So conservative fields, why do we actually care about these? That's a good question. But conservative fields have a lot of very, very nice properties that make vector calculus so much easier, particularly with line integrals. So if we take the line integral of a conservative field, we have this really nice theorem called the fundamental theorem of line integrals, or fundamental theorem of line integrals on conservative field, whatever you want to call it. And it says that if f is a conservative field, such that we can write it as our nabla phi over some curve that has a start point, say like the curve looks a bit like this, C of A, C of B, then if we evaluate the line integral, we don't have to do any work. If we know what nabla is, we just plug the endpoint in, we plug the start point in, and we just subtract them. So it's this really, really nice theorem. This is technically the same thing as the fundamental theorem of calculus. We see that we integrate f dx with respect, like from a to b, it's just f of b minus f of a. This is the same thing, just in a different context. And a unique consequence of this theorem is that if we draw a closed loop, our start point is our end point. So that means that these will be the same, and we're just subtracting, the same thing from itself, so to be 0. So in other words, and if we're in a closed loop, we draw a little circle here. So this is, of course, given that f is a conservative field. So really neat consequence of this theorem. So yeah, we can think of this much like the antiderivative. So here we've got a practice problem here, and we've got a scalar field, and we're told that f is nabla phi. So we can immediately deduce this is a conservative field. Okay, it's going to make our life so much easier. So the first part is, what's the curl? Okay, so we saw the curl was this big, like matrix determinant thing. Pretty yuck equation. I don't like determinants. I don't like matrices. But it's a conservative field, so it's just 0. Doesn't rotate. So we can immediately, that's half the question done. So yeah, and this comes from this. This directly means that it's conservative. This is putting the English into maths. So that means the curl is always 0. Sweet, that's half the question done. Okay, so what's the line integral? Okay, well, we can just use our fundamental theorem of line integrals, which means that, it tells us that if we go from this point here to this point here, it's just going to be phi of this minus phi of this. And that's just a matter of plugging numbers into an equation and subtracting it. And it saves us having to do any, yucky parameterize. We don't have to parameterize anything. We just plug numbers into an equation. That's the whole question, right? So yeah, fundamental theorem of line integrals, very, very important. This thing will save our life. And we can see there we just plug the numbers in, and we end up with 2. So it saves us having to do this long-winded parameterization. Or what's c? Or how do I? Okay, now work out the line from this point to this point. None of that. We know what phi is. We plug it in. Happy days. No calculus required. Okay. So here's another question. We've got a vector field given by this, pretty yucky expression. Now we want to show that f is conservative. So this time they don't tell us that it's nabla phi. We don't get the easy way out. They want us to show that it's conservative. Okay. And well, at least they're quite nice, and they tell us how to do it. We evaluate curl. So let's do that. Let's evaluate the curl. So from slide 60, or if you can recall, if you've got it memorized, the curl is given by this matrix determinant. So it's just ijk in the top row, our partial derivatives, our partial derivative operators, whatever you want to call them, in the middle row, and then our vector field components. So these are the x, y, z components of the vector field, respectively. And now it's just a matter of computing this determinant, which is quite tedious, but as long as you know what you're doing, then it's a bit of calculations, but we can eventually get to the result. So we sub in our x, y, z components. So this is f1, f2, f3 into our vector field, and then we compute our determinants by cross multiplying them and grouping them with our respective ijk basis vector. So we get that the curl is this monstrosity here. And I'm not gonna like sit here and line by line go through the calculation, but we can see that we just cross multiply these terms here and then subtract them from each other, which we get from the minuses in here. And it's just a simple matrix determinant. There's just a lot of terms, and that's what makes it quite yucky. Now, alternatively, there's a different way that we can calculate curl, and it's much, much nicer. So I know everyone here, we're all engineers, we're lazy. We don't like to actually put work in. So we're going to say that the curl here is, and then xz squared. Sorry, my handwriting is really messy. I'm trying not to put my hand on the tablet because it's just going to freak out. 2xyz Okay, so you may remember this from Math 1B. They may have taught you this shortcut. To evaluate the curl, we just cross-multiply this and then cross-multiply this. Subtract them from each other. Okay. So this thing here, with partial of this with respect to y, is just going to be, we just get rid of the y. We don't really need that. So it's just 2xz. Okay, so the partial derivative of this with respect to z, okay, well, we just bring the 2 down, so it's 2xz. And that's awfully convenient. Now the next term we get by multiplying this and multiplying this. And we always go, it has to be dz first, because the cross product is not commutative, unfortunately, so we can't just flip it around and it'll put a negative sign on there. So we partial with respect to z here, we have yz squared, so this will be 2yz minus partial of this with respect to x, just get rid of the x. So it's just 2yz, and then the 3 disappears. And then, last but not least, this term and this term. So this with respect to x is just going to be z squared. This with respect to y, just get rid of the y, z squared. So it saves us having to do all this like matrix determinant nonsense, and we can just deduce, oh, okay, this is the 0 vector. Sweet, because all the terms cancel, happy days. And that's like 2 lines of working. So yeah, it's just a bit of partial derivatives in your head, but nothing too crazy. Okay, so we've deduced that it's a conservative field, the curl's 0. Perfect. Okay, so that means that there exists some scalar function phi such that f is nabla phi. So we're going to keep that in the back of our mind because we might have to use this later. So we've got that the path that we're calculating the work over starts at this point. Okay, this is important. And it subsequently travels anti-clockwise 4 complete revolutions around this circle within the plane z equals 7. Okay, there's a lot of information. And it returns to the point that it started at. That's very important. It returns back where it started. This is the kicker of the question. And then it moves diagonally in a straight line. Hence, evaluate the work. Okay. So I'm going to rub this out because we don't actually need this. Because if you'll remember the really nice property about doing line integrals of conservative vector fields is that if it ends up back in the same point it started, 0. The whole thing's 0. So we can say that, well, FDR is C1, which is the 4 revolutions it does around the circle, and this is the straight line that it moves in. And I'm going to put a circle on here because it's going in a closed loop. And we know that the line integral of a conservative vector field on a closed loop is 0. Bang. So all this confusing nonsense about, oh, x squared plus y squared is 25, we have to now parameterize a circle that's like lifted up, z equals 7, we don't have to worry about that. We only care about the straight line that it travels along. So, yeah, here we go. We don't need to go through the trouble of parameterizing our curve. We can just find this, right? We actually don't even have to do any parameterizing. Of course, we do want to worry about our start and end points because it travels in a straight line. So therefore, there's going to be some work done because it doesn't return back to its initial point. Okay, well, we can just find what phi is. Okay, well, how do we find phi? That's the real question. Well, we know that phi f is nabla phi. So if we just label some arbitrary function phi, we can equate the partial derivatives of phi, that being d phi on dx, d phi on dy, d phi on dz, is equal to the x, y, z components of f respectively. So we get this nice system of equations. And that is, of course, matching up this with this, matching up this with this, matching up this with this. Now, I'm going to briefly go through a systematic way to do this, the proper way, and then we'll do the engineer's way after. So we can start off by, saying that, well, looking at our first equation here. And we'll say, okay, well, del d, whatever you want, partial phi over partial x is yz squared. Okay, so if we, I don't know what you want to call it, partial integration, I don't know, reverse partial differentiation. We just integrate and just pretend it's, pretend that the y and z is constant. So we end up getting this. But then since we've got this, it's reverse partial differentiation, we have to tack on not just a constant, but a constant function. Because if there's a function in terms of y and z, it'll completely disappear. So now we can go through this like cascading process of working out what cyz is, and then working out what cz is, and then hence finding a total function. And that is, of course, by looking at our other partial derivatives. Because we have unknowns, we have 2 other equations, we can work everything out. Okay, so we just worked out that our function was this, plus the constant. So if we know from our vector field that d phi on dy is our y component, we can equate these two. These are the same. Or if we take the partial derivative, this is the same. And we end up with an equation like this. And then we just cancel this, and we end up with this here. So then we can say, okay, well then if we just reverse partial differentiate, we get a half y squared plus some constant in terms of z. So we're reducing the variable by 1 each time. And then we do the same thing. We now look at our third equation, this one here. And we say, well, now we know that our new function, or we know this. Sorry, this is, whoops, not that one. Our new equation is this. So then if we just partial differentiate this with respect to z, it'll be equal to this here. And then we can finally work out what cz is. So we get c dash z by equating and cancelling terms and doing all this, equating both sides. And we get c dash z is 3. Okay, so then if we just, this time we don't even have to reverse partial differentiate. We just straight up integrate with respect to z. So we get 3z plus some constant. So now we mash all of it together and we get our final function here. Right, that's a bit of effort, and I don't know about you guys, but I personally would not want to sit down and have to go through all of this pain. So I'm going to show you a much easier way to do this. So that's the proper way. That's the proper setting out. You should really, technically you should do it that way, but it's fine. So if we just look at this first one and we think, okay, what if we reverse partial differentiate? Okay, so we just tack an x on there. And this would be in terms of y and z. And then we just do the next with the same, we do the same thing with the next function. So we get, with respect to y, this becomes x, y, z squared. And then we do the same thing with the last one with respect to z, so that it becomes a z squared and the 2 goes. And now, oh, whoops, I missed a term. The 3, we integrate that with respect to z. So this would be 3z.
What about the y?
Oh, my bad. Oh, sorry. Thank you for pointing that out. So this would be plus. Now, we know that all of these, since we've undone the partial derivative, they're all equal to phi. These are all the same thing. So then we just do, we just kind of like look at it, and we just do a, I guess, as mathematicians say, by observation. So we get this is all the same. Okay, so this has to be in our phi. Okay, well then we've got some function of y squared. Okay, so that could fit into this, since this can be a function of y. That could fit here, since this is also technically a function of y. And then this missing function that has a z in it is just accounted for here. So these additional functions that pop up in this, so like the 3z is unique to this one here, but that's just hidden inside of this. And this y squared here is just hidden inside this and hidden inside this. So we just straight up match the terms up and just go, oh, well, phi is just xyz squared plus a half y squared. And of course, plus some constant. So what we've seen is we've just done like 3 lines of working and we've just got to the answer. And if we go all the way back down, we get the same function. It's the same thing, but it's so much less effort. So that's if you want to be an engineer and do the much quicker way, the much more simpler way, right? Not as rigorous. You just do it that way by inspection. Voila, formula. Out of thin air. And now, of course, we have to calculate the work. And we don't have to parameterize any curve because we just have the points. And since the field is conservative, we can just plug this in by our fundamental theorem of line integrals. And then it's just a matter of computing. So we're plugging these values, just to show where we're plugging this into. These values are going into here. So we plug these into this equation, and we get this. So we can calculate that the work done by this particle that spins around 4 times and then just flies off in some other direction diagonally, it does that. That's the work. That's the work done on the particle. There's some really nice assumptions that we can make in there that just simplify everything. And that's what's really nice about vector calculus. All right, so we're going to move away from vectors, and we're going to just look at double integrals. So we're still in the region of integration and calculus and all this cool stuff, but now we're looking at integrals that don't involve vector fields. So we're told that we've got this integral, this double integral over some region, omega. Is it omega or omega? However you want to pronounce it. So we've got this region, and it's bounded by this parabola and this y equals x and the y-axis. So what this region is going to look like might be a bit hard to picture at first, but it looks a bit like this. So this is our And then this is, of course, just our y-axis. So we've got this region bounded. And I'm going to put this in here. It's a bit wonky, but it's close enough. And we want to try and evaluate what the integral over this region is. Now, the nice thing about this is we have two ways to work it out. We have options. So we can either calculate this first integral, or we can calculate this second integral. And I'll show you where this comes from. So we say that using a bit of geometry, this is 2 and this is also 2. That point there. So we can say that either x is bounded between 0 and 2, because that's the furthest x goes along, and then y is constrained by this curve here and this curve here. So we'd say that the bottom curve is just x. So we have this, right? This is one way we can do it. Alternatively, I don't know, if you hate yourself, you can do it this way. You can like partition it up and then express it as like two separate integrals. But I don't know why you do that. I don't know, if you're unsure on your answer and you want to make sure that both ways work, go for it. But for the sake of ease, like the second one is what you get when you partition it up into two separate regions. You have to do two separate integrals. Nobody wins, right? So that's why we do it this way. We're going to do it like this because this is just a lot easier. So yeah, it's much simpler. It's much simpler. I'm sure you all agree. It's much simpler, and we don't get like square roots in the bounds as well. Like this has square roots and it's two integrals. Like, I don't know. That's absolutely horrific choice. Absolutely horrific choice right there. So we can just say that, well, this integral over this region omega, we can just substitute the bounds in and put our dy dx in. So this is obviously our y bounds on the inner integral, and that is, so I'll highlight this in different colors. So we have dy on the inner integral with the y bounds, and then the x bounds were 0 to 2 on the outer integral, because our dx is on the outer area. So, and then it's just a process of computing the integral, right? We now have a simple integration problem. We first integrate with respect to y. Okay, so that y squared, this is now just a high school integral. So this squared comes to 3, you divide by 3, reverse power rule, yada yada. Plug these numbers in, or these, I guess, functions in, into y, and then we get a pretty yucky expression. We end up with this, which isn't the best. It's just, I don't know, you just throw the reverse chain rule at it and it comes out nicely. So by using the reverse chain rule on this term, so the single variable, the high school reverse chain rule, this goes to this, and then this is just a simple power rule integral. And then obviously you raise it to the power of 5, divide by 5, and then you multiply by the 3, and it becomes 15. So we get this expression, and then it's just a matter of plugging numbers in again. So we plug in the 2, we get some negative number, and then we plug in the 0, and then this thing like gets very, very big, and then it tips over to a positive number, and we get this 256 on 5. That's what that integral evaluates to. So fairly simple. We just observe the region and pick either x or y to be constrained by functions, and then integrate. So we do whatever's nicer. Now, we have another trick up our sleeves when it comes to double integrals. Sometimes we get r squareds or x squared plus y squared, all this stuff. So we can do a polar coordinate substitution, which means that we just change x and y to r and theta. And if we do that, we can't just change dx dy to dr d theta, we have to put an r here. So an integral like this is the perfect example of where we'd use a polar coordinate substitution, because this will evaluate to r squared. When we say let x equal r cos theta, let y equal r sine theta. So anytime you see this, dead giveaway, it's polar coordinates. Okay, so we want to try and convert this region, which is the circle, there's a circle in the xy plane with radius capital R, to a polar coordinate region in terms of r and theta. So I think you'll agree, it's a circle that goes from 0 to r. So r is between 0 and capital R. And we're told that it's in the first quadrant. So the first quadrant is the first pi on 2 radians, or first 90 degrees of our xy coordinate plane. So that's why theta is bounded between 0 and pi on 2. So that's where we get this, that's where we get this. So this will become our integral bounds. So we just do the, in our head, x equals r cos theta, y equals r sine theta. This becomes an r squared. dA becomes an r dr d theta, and we end up with this. And then we just plug our integral bounds in, which was this inequality here. So we get this integral that we can evaluate quite simply. It's a standard integral, right? So we've just done this. And we've taken it from something that's a bit yuck to something that we can easily evaluate. So we integrate with respect to r first. So we divide by the derivative of this, and we end up with -1/2 e to the minus r squared. Plugging these in, we end up getting this. So, I mean, you can get rid of the negative and you can flip the bounds to get 1 minus e to the minus r squared. And then we have the half. Now integrate with respect to theta, we end up with a pi on 4. Because there's nothing in terms of theta in here, so it'll just be pi on 2 times this, which we get pi on 4. Okay. So we've got this identity, right? And we want to try and leverage this. We want to try and work with this. What can we do here? So how can we use this to calculate this, right? Well, it's going from 0 to infinity. So x is completely, or x interval is 0 to infinity. So if we think about it, our r is technically unbounded. R goes from 0 to infinity. So in other words, we take the limit on this expression here. Or we can use this expression and we can take the limit, right? So if we take the limit as r goes to infinity, we end up with this integral here. Because our bounds then become infinity as we take the limit. And this term here gets insanely large. And then since it's to a negative power, it becomes insanely small. So it just goes to 0. We don't have to worry about that. So then we're just left with pi on 4. Okay. Now you'll notice that e to the minus x squared plus y squared is a separable function, right? Which means that it can be expressed as the product of some function in terms of x and some function in terms of y. And the really nice property about these separable functions is if we have it in a double integral, we can split the two integrals up, which is exactly what we do here. So we split these up into two integrals, and then we can recognize that this integral here, if we just say let x equal y, it's a thing called a dummy variable substitution. We just say let x equal y. Therefore, dx is equal to dy. Therefore, the x limits is equal to the y limits, right? So we get the exact same integral, but instead of a y, we just write an x. So these are the same integral in disguise. The letter that we give here is just arbitrary. So we can just replace the y with an x, and then we have the integral squared. And then now we just square root both sides. And we get that this Gaussian integral is what it's called. This is a Gaussian integral, is equal to square root pi on 2. So it's a really neat thing. We can leverage all these identities using our polar coordinate substitutions, and we get this really nice result. So that about wraps up double integrals, vector calculus. So I'm going to pass this on to Rosh to talk to you guys about Laplace transforms.
Sorry. Hey guys, today we will be talking about Laplace transformation. I hope you are excited because I am. This is definitely my favorite topic in the course. So, let's start with a brief introduction. So basically what the Laplace function is that it converts a function of time into a function of space. So like, for example, you can probably convert like waveforms of time into like some frequency function if you do like eng. Yeah, and basically what Laplace is it is defined by the integral from 0 to infinity, the function, and then e to the minus st equals to fs, right? Sorry, it's the improper integral. So since now we know what Laplace is, let's do some very, very simple examples. So using the table of Laplace transform, evaluate the following. So using the table, what would E3t would be? Good job. It is actually 1 on s plus. It's actually minus 3 because, yeah, because over here there's a 3t and in the table it's like e minus t becomes okay. How about sine 5t?
5 on s squared plus 5 squared.
Good job. Okay. Now, how about number 3?
5 on s plus minus 3.
Right? 5s minus 3 plus, and then 10 s squared, s squared plus 5 squared. So what you did in question 3 just shows that you just did a linear property of Laplace transform. So if you don't believe me that Laplace transform is linear, this is the proof. So you have to believe me now. Yeah, so basically what it kind of means is that, let's say you have 5 of a function, like 5 times whatever function you have. If you want to find the Laplace of that, it is just 5, the Laplace function, so it's just 5 fs. Right? Okay, so let's do a question. So using the table of Laplace transform, find the Laplace of t plus sine 2t plus e minus t. Okay, how would we approach this question? Right? So the thing is, because of linearity, it's also distributive. So what we can do is we can just find the Laplace of t plus the Laplace of sine 2t, and then the Laplace of e minus t. So you know that the Laplace of t will give you 1 over s squared. Laplace of sine 2t will give you, will give you 2 over s squared plus t squared, and Laplace of e to the minus t is 1 over s plus 1. So therefore, the function would just be, the Laplace of this function would just be that, by doing it one by one. So now we are going to move on to the Heaviside function. So the Heaviside function is also known as like the unit step function. So you can think of this as a function that turns on and turns off. So like, well, the only example I can come up with at the top of my head right now is that if you do a like eng, this could be used to represent like the current turning on and off. There's definitely going like more examples to it, but it's the only thing I can come up with right now. If you do have something else, feel free to drop it down in the comments below. Yeah, so that, this is 1, and then this is 0. Yeah, where, oh, sorry. So the thing about the unit step function is that we can manipulate and we can shift and manipulate it. So for example, let's try to graph like, I don't know, ut minus 1 minus ut minus 2. So we can take like a very like high school approach. So first of all, we can draw first ut minus 1, where ut minus 1 would just be, it would be 0. It would be 0 all the way until it reaches 1. And then now when it touches 1, it like turns on. Right? And then similarly for ut minus 2, it turns on at t minus 2. So what this means is that, so when we combine this, what happens is that, let me draw the graph really quickly. Is that, so as the function approaches 1, as it approaches 1, it'll be 0, but then at 1, it's going to turn on. And then as it approaches 2, it'll still be 1 because, well, this is still 1. And then after that, the moment as it touches 2, it will go back to 0. So one way we can, a way we can represent this is ut minus 1 minus ut minus 2 is 0 for when t is less than a. It's 1 for when t is between a and b, and then it's 0 when t is greater than or equals to b. So this can be generalized into ut minus a minus ut minus b equals to 0 for when t is greater than a. It's 1 for when it's between a and b. Then it's, and it's 0 for when b is greater than t. So the beauty of the unit step, the beauty of like the Heaviside function is that you can like manipulate it. So let's say we want this to be 3 instead of 1. We multiply this whole thing by 3, and this will be 3. Or let's say we want it to be like 2x plus 1. This will be 2x plus 1 as well. So really, yeah, it's quite a cool function. So the Laplace of that will give you this. Very nice. And then we can also express other functions in terms of the Heaviside function. Sorry, do you have a question? Oh, no? Oh, okay, sorry. Okay. So the first shifting theorem. So sometimes the Laplace transform that we obtain isn't just the n, isn't just that. We have to shift it. So what we can think about it is we can think that this is a translation of your time component. So how this happens is that, let's say you have a function, and then you see that it is multiplied with e to the whatever st, right? Oh, sorry. You have a function, and then you see that it's getting multiplied by e to the minus like at, like where a is any constant. So what happens is that, like, when you derive it, which you will not, but this is just to show, it shows that you are shifting like the exponent component. So that way, because of that, we're going to do some amazing maths happens, and you just get a function, the space function plus whatever the negative of the exponent that you get. So that is it. That is the first shifting theorem. So let ft be a function such that Laplace transforms that, then you will get that. So obviously these words, when I first read it, it made no sense. So we are going to try an example because, yes, so I took this straight from 2023 term 3 question 1 from the past paper. So sorry guys, spotted a typo, Laplace with a capital L. Use this table of Laplace transform to evaluate the following. So e exp t to the 3 cos 2t. So, because this is in Mobius, we are going to try to rewrite this into a form that we can see better. So Laplace of e t over 3 cos 2t. So this is like in the table of Laplace transform we have. This is very similar. This mimics the e minus at ft, right? Okay, so the exponent of the the exponent in the function here is going to cause a shift in the cos in the cos 2t in the space function in fs, so the space function, right? So normally, let's think about it in terms of cos 2t, because we know that the exponent is going to cause a shift in the fs. So we know that the exponent is going to cause a shift in the fs of cos, right? So let's first find the function of time. Sorry, the function of space of cos 2t. What will we get? Right? So you're gonna get s over s squared plus 2 squared, right? So let's think about it in terms of first shifting theorem. You have an exponent of you have a shift of e to the power t over 3. So therefore, in terms of fs plus a, this is your fs, right? So your a is minus 1 over 3. So what happens? So therefore, the Laplace of e t over 3 cos 2t would just be s minus third over s minus a third squared plus 2 squared. That's it. Very simple. Yes, very nice. Yep, got it here. Okay, so now the second shifting theorem. We will not stop at just one shift. We will now have 2 shifts. Hell yeah. Basically what the second shifting theorem is that you're kind of shifting the first shifting theorem. So you're shifting something that's already shifted by another shift. So that probably makes no sense. But again, if you don't believe me that we can do second shifting theorem, this is how we do it. So it is a result of the Heaviside function as well. And yeah, we get this. So again, we're gonna do an example that shows us exactly what the second shifting theorem is, because I feel like showing is probably would make more sense than me trying to explain what the second shifting theorem is. But if you look into your Laplace table of transformations, it's right below the first shifting theorem bit. Okay. Before we do that, so the Laplace second shifting theorem is this. So how do we spot this? So if there's a cut at A, then the second shifting theorem applies. So like one way we could look at this is that, okay, we see if we have a function, and then if we see there's a function that's already shifted, and then we see that it's multiplied again by e to the power of whatever s, right? So most often times in our course we're gonna do it in reverse, but there's still going to be questions that ask you to do the second shifting theorem by hand. So when computing the inverse of Laplace transform, make sure to look for the exponential functions inside the inverse functions. So that is a clue. If the inverse function has an exponent to it, then it's definitely going to be second shifting theorem. So what do I mean by that? Let's look at this. So we can see that there's already a shift in here, and now we see that it's getting multiplied by e to the 7t. So what does that mean? There's two shifts. Oh, second shifting theorem. Very nice. So first of all, we know that the second shifting theorem, like, it looks a lot more like this. But so far, this does not look like this. So we want to rewrite it in a way that it looks a lot more like this. So we know that there's a shift at t minus 4. So therefore, let's rewrite that. So let's add t minus 4 into that. But then we can't just simply add numbers in, right? Like, it needs to be conserved. So we're gonna, over here, we're gonna have an extra of like minus 28. So to mitigate that, to like cancel that out, we add 28. And then t minus 4. And over here we can spot like a linearity rule. So 28 is a constant. So you take it out. You can ask what their favorite color is or something, I don't know. And then 7t minus 4, t minus 4. Right? So once we get this is, so we have this. Okay? The thing is, so if ft, oh, sorry, I forgot I wrote it down here. Whoops. So if ft is e to the 7t, so ft minus 4 should be e 7t minus 4. And then, you know, because we want to put it into this format, et minus 4, it's that. So we will get that through because the Laplace table is for, because like the second shift thing is like, we have like E, AS, FS, right? So this one will become this one and this one, okay? So that way, the Laplace of e to the 7t would just be 1 over s minus 7. So we would just get this. Okay? Is everybody clear so far with the shifting theorems? Anybody have any questions about it? No? Well, I will bring good news because we are only going to have 2 shifts. So that's all the shifting theorems that is. Yay! Okay, so now we are going to talk about inverse Laplace transform. So the beauty of Laplace is that it's invertible. It's reversible, not invertible, sorry. Yes, so where would this be useful? Where we are about to find out. So we typically use the first and second shifting theorems to simplify our expression. So sometimes they'll give you like a big function and then you go like, oh, this looks like it's from the second shifting theorem, or it looks like we're gonna use the first shifting theorem, and then use it to simplify it, and then you find the inverse of it. So the table of law, sometimes you might need to do extra work to write the table. Yeah, so this is quite important because it's really hard to figure out which table to use. I'm sorry, not which like line of the table to use. But if you go like, this looks like, I don't know, this looks like s over s squared plus omega squared, which is like cos omega t. If you rewrite it in a way that makes it really obvious that, oh, it is exactly that, is gonna make the process a lot easier. So we're gonna go ahead and do an example of how we're gonna simplify the Laplace, our inverse Laplace. So there's 2 ways. So when we see that there's like a quadratic, like when there's like a quadratic at the bottom, you might freak out and go like, oh my god, what do I do? Because that's what I did. But then, do not fret. We are going to calm down, going to take a deep breath, and we are going to solve this because anything is possible. So first of all, we're going to look at this and we're going to like, let's try to complete the square, because completing the square puts it into like s plus whatever squared plus a number, and who knows, that number could be a squared or something, and that's very similar to like the Laplace of like sine and cos. So s squared to s plus 5, right? When we do completing a square, we will get s s plus 1 squared plus 4, and well, 4 is 2 squared. So that way, what we can do is that we can rewrite this expression as, like that, because, because we saw that there's a shift in, because we saw that it's s plus 1 squared, we want to rewrite it in a form that's like a lot easier for us to do the inverse of. So see, so essentially, like, yeah, s plus 2 is s plus 1 plus 1. So because it's a numerator, we can split it up, and we get this. So now let's try to find the inverse, the Laplace inverse of all of this. So first of all, let's find the inverse Laplace of s plus 1. So what does this look like? What Laplace inverse does this look like? Cosine, right? But is it just cosine? It's a shift. So what is this using? Which theorem are we using? First, second shifting? Which one? First, right? Because there's only one shift. So what would this become? So cos 2t, because this part is the omega, 2t plus, so we would get, e to the minus t cos 2t. Okay? And then, what does this look like? Sine. Good job. You guys are totally slaying this. But is it just sine though? No, right? There's a shift. But here's the thing, like in the space function in the Laplace of sine, what we would they give that it's omega plus s squared plus omega squared. But if omega squared is 2 squared, so omega is 2, the top is not looking like a 2. So what we can do is we can just times it by 2 over 2, or like times it by 2 over 2, and we can do that, and we can do half. Wow, we're adding random numbers in there to make it look like it's the same, but it's actually the same thing. Big slay. Anyway, just gonna cast this aside. So that way, what we would get is half e minus t sine 2t. Okay? Is it? And then if I move to the next slide, it'll show you that it's exactly correct. We are exactly correct, sorry. And then that way we will have, so therefore the inverse Laplace of whatever question we got is just that, which is what we broke it up and did it like slowly, and then we get this. Honestly, I probably would not simplify it, because like but if you want to simplify it, go ahead. I guess when you're doing these kind of questions, don't forget to put the asterisk with the t, and don't lose marks in Mobius. Yes, that's all I have to say. So next one. So what happens if we can't complete the square, or if completing the square looks like it takes too much effort? So this is an example of that. So let's find the inverse Laplace of 7e to the power minus 2t over whatever that quadratic is. So let's look at this. Does this look like the first shifting theorem or the second shifting theorem? The second one. Why? Right? So there's an e, there's an e to the power of 2s, but then like this part is also like some shift. So there's two shifts, so it's the second shifting theorem. It's actually a nice naming thing. Two shifts, second shifting theorem. Anyway, so using the second shifting theorem, sorry. So we get that. And then so So first of all, since we already know that we have e to the power of minus 2s, which is very similar to the part of the second shifting theorem, where it's like e minus as fs, right? That part. So we know that that is that. So let's find f. Let's find the space function of this. So to find what we're going to do is we're just going to find the Laplace of 7 over s squared plus 5s minus 3. Okay? No? Okay. So, sorry? Yes? Oh, sorry. Yes, 2s squared. Whoops. Sorry. Haha. Whoops. Anyway, so in our example, so this is just the Laplace second shifting theorem. So we know that a is 2, and we can also see that plus the function of t is this. So now we have to find the inverse of 7 over 2s squared plus 5s minus t. Sorry, minus 3. Gosh, t's and 3's. So we're going to do partial fractions. Yay! Okay, okay guys, it's not that bad. Don't stop frowning. It's okay. So since first of all, to do partial fractions, we have to split the quadratic. So we know that 2s squared, sorry. You know what, let's make it pink. 2s squared plus 5s minus 3 would factorize the quadratic and it would become 2s minus 1 and s plus 3. So therefore, we would get this fraction. And then, you know, using rules of partial fractions, we would get a over 2s plus 1 and b, like, so whatever coefficient, s plus 3. So this is equivalent to finding this, which is just this. And then since we know that, so we know that because the coefficient of s is a plus 2b and there's none for s, we can assume that this equals to 0. And then this is just by itself, so it must be like a number, like a scale, like whatever. So this is going to be 7. So what we can do is a plus 2b equals 0, and then doing that. And then eventually we will find that a is 2 and b is minus 1. There we go. I'm sorry for not going through this for not like writing it out with you guys, but you know, it's a long process, and who wants to watch me do that? So that's very nice. So what does this mean now that we have separated our big fraction into more digestible fractions? Well, we now can find the inverse Laplace of this. Hold on, let me write it a bit nicer. Okay, so let's try to first find the inverse Laplace of 2 over 2s minus 1. So 2 over 2s minus 1, we can simplify it. We can just simplify it, you know, divide it by 2, and we will get 1 over s minus half. And this is very similar to 1 over s plus a, where a is minus half. So therefore, we would get that the inverse Laplace of 2 over s minus 1, which is the Laplace of 1 over s minus half, we would get e to the half t. Everyone agrees? Because you should, because this is the answer. Anyway, so now let's find the Laplace of 1 over s plus 3. So that is just that. Amazing. So therefore, So we know that the first fraction, it gave e to the t. And then keep in mind that this bit is a negative. Don't accidentally add it like I did when I first did it. So minus e minus 3t. That is your inverse, right? So that's like 3/4 of it done. So now let's consider what it does now that this one would be multiplied by e to the minus 2s. Now let's consider what's going to happen if we do that. So because that will cause a shift in the, because the exponent in fs, so the space function, is going to cause a shift in the time function when we do the inverse. So that will cause a shift in in ft to make it minus 2 and ut minus 2. So like when we look into the Laplace second shifting theorem in the table, it's like, I'm just gonna write it out. It's minus AEST fs, so it looks a lot like that, and that will become f t minus a u t minus a, so Heaviside function. So that way, whatever is a t, we have a t in our inverse Laplace that we found for 7 over 2s squared plus 5s minus 3. So this, we just chuck in t minus 2 to where the t is, and then put in a, because this is the formula, and then boom, that's it. We have solved the question, and that is how you use the second shifting theorem to inverse the space function using Laplace. Now, that is not it, guys. If you think that is over, you are so wrong. Because we are Math 2018-2019, we love ODEs. We have to use ODEs with everything. So again, it is a lot of just knowing what it becomes, and then just constantly applying it. So we recall that we have two differential Laplace expressions. So in your, I hope you're opening the Laplace tables of transformation as well. It's like right below each other, but it's right above the first shifting theorem. We know the Laplace of the first differential is SFS minus when the function is 0, and then the second differential is S squared Fs minus S times whatever the differential is, whatever function is when it's 0, and the differential when it's 0. So therefore we have a form of that, and then using so if we have let's say a differential of this, right, we're like, oh, it's A times the second differential plus B times the first differential plus constant. We can use the linearity to do this. So again, all rules of Laplace still apply. So we need to substitute everything into the differential equation and allow us to solve Fs. And then with that, we inverse it and then obtain the original function. So again, to fully understand this, we shall do an example. So use Laplace transform method to solve the initial value problem. Okay, so let me just write it down a bit. Okay, so let's do this. So y differential plus 2y equals to 4, and when y0 equals to 1. So we're going to find the Laplace of y, the differential of y plus 2 plus of y equals to the Laplace of 4. So this one will give you s ys minus y0. This one will give you plus 2 ys, because this is just the Laplace of the function y. So function y, function of space function of y. And then the Laplace of 4 is just 4 over s. So we know that y0 is 1. Sorry. We're going to move that to the other side. So what we will get is we'll get s plus 2 ys equals 2, 4 over s plus 1. And then we know that the plus function of s is just 1 over s plus 2. Right? So now we have the space function of y. So all that means is that we have to just invert these functions, inverse these Laplace functions back into the time function, so into ft, and or in this case yt, and eventually we will know what yt is. Okay, so inverse these. Let's inverse these. So first of all, let's expand this. So when we expand that, when we expand this, we will get this, and then you have to trust me on this, but when we do the partial fraction, we'll get that, but just trust me. But when we partial fraction that, we will get this. If you don't trust me, you can do the partial fractions. You can do the partial decomposition yourself. So now all we have to do to find yt is you just find the inverse Laplace of 2 over s minus 2 over s plus 2 plus 1 over s plus 2. So it's actually quite simple, since we can just split it up. So yes, so the inverse of 2 over s is just 2. Very nice. And then for the second expression is 2 over s plus 2. So what we can do, to make it look a lot similar, what we can do is we can just do 2 1 over s plus 2, which looks very, very similar to e to the minus at, like that bit. So therefore it is just 2e to the minus 2t. And then same thing with the third expression. Right? So therefore we just add all of these up. We just add all of these up. We will get this 2 minus 2e, and then you're like, oh wait, isn't this the same thing? Oh, okay, minus it. Eventually you will get 2 minus e to the power of minus 2t. Okay, everybody understand so far? Okay, so that is actually all that we have to do with Laplace transform. But I mean, it's university maths. They're not just gonna give us one very nice problem. We have a final boss problem to tackle. So I'm pretty sure everyone in this room is very familiar with this question, and we're gonna see how Laplace transform is actually used in the exam. Okay, so first of all, let's read this question. So the reason why I say it's a final boss question, because we have ODEs, we have Laplace, and we have matrices, and damn, all 3 topics in one. Amazing. So consider the system of differential equations. Let function of s be the Laplace of xt, ys, that be Laplace transform. So A, Saranjeev believes that the system can be written in the following matrix form after applying Laplace transform. Help Saranjeev by writing out the matrices A and B. Okay. Let's go to the next page. So A, we have to find A xy equals to B. Also, guys, if like you feel lost or any time as I'm explaining, feel free to just like ask any question, or if you want me to like repeat anything or like simplify what I'm saying, just say it out. It's fine. Okay. So how to do that? First of all, they want you to find the Laplace form of each of these ODEs. So let's find the Laplace of dx over, no, sorry, Laplace form of that. Okay, so how will we do this? So we know that this is the first differential. We know that this is the first differential equation, so we're going to use s xs sorry, minus when x is 0 equals to 16 ys plus 29. So what's the Laplace transform of sine 6t? So it's going to be 6 over s squared plus 6 squared. So we know that when x is 0, it's just 0, so we can just very nicely just cancel this out. And then that way, and then let's put the x and the y's together. So what we will get is, for the first one, we get s. Bro, I'm sorry, I just realized I used brown and now I'm using black. So now we have s xs minus 16 ys equals to, what's 29 times 6? 174. S squared plus 6 squared. So now let's do dy dt. So using the first order differential equation, s ys minus y0 equals to minus xs. So we know that y0 is 1. So let's rearrange it into similar form to this. We will get s. Well, let's put the xs first, because that's just 1. Okay, so what does this look like? Doesn't this look like a system of equations? So if this was a system of equation, right, wouldn't this just be s minus 16? Sorry. This would just be s minus 16, and then we have 1 and we have s. Oh, sorry, it looks a bit big. Let me just write out a bit nicely. Sorry. For s, and then if we multiply it by and that's how you rewrite a system of differential equations into Laplace form, and you chuck it into the matrix. Okay, so the thing is, the question asks you to find a and b. So a is through observation, a is s 1 minus 16 and s. So since the exam is in a Möbius, we're going to use maple syntax. S, if I'm wrong, call me out, okay? That. And B, I remember they told us to just do 174 over S 2. And then 1. Okay, so boom, we solved the first question. And if I remember correctly, when I did this, my Mobius was green, so I'm going to highlight it in green. Because let's all agree, we all get that rush in dopamine the moment like it goes red, then it changes to green. You're like, oh, yeah. Okay, so see, that's not. Oh, not OneNote. Sorry, GoodNotes. So there's a second part to it, because it's an exam question. So now we have to find x. Oh. Now I have to find xs and ys. Okay. Okay. So now you might be like, oh, surely I can just like rearrange whatever's in rearrange whatever in here. You can, but there's a simpler way to do this. The whole point of doing engineering maths is through finding the simplest way to do something. So there's actually already a hint within the question that they gave. So a xy equals to b, right? And or like one way we can rewrite this is like that. So what we can do is we can multiply both sides by a minus 1. So I'll use a different color for that. So a minus 1, a xs ys equals to a minus 1 b. Oh, look, a minus 1 and a. That's just the identity matrix. So that means that, oh, it's just 1 by 1, so cancels out nicely. So we get xs ys equals to a minus 1 b. So using the previous seminar, we would know how to find a inverse. So a inverse is just 1 over the determinant of a over, so it's, the thing is, it like the s and s like flip, so because it's the same, doesn't look like it flips, so the s and s, and then we multiply, so these flips, and then after that we multiply these by like minus 1. So, whoops, sorry. This one becomes 16. This one become minus 1. So determinant of a is just, well, AD minus BC. So the determinant of a would just be, so let's just put that. That a is s squared minus 16. So it's just plus 16. And also it might be useful to just write this out as 4 squared. So you know what? Let's write it out. xs ys equals to 1 over s squared plus 16, s minus 1, 16, s, multiply it by b, and b is this. Square plus 6 squared, and 1. So, you know, we're going to just multiply this through, and when you multiply this through, you know, we'll just multiply this through, and then multiply this through. You get xs is 174s over s squared plus 6 squared and then don't forget to include the determinant, s squared plus 4 squared plus 16 over s squared plus 4 squared. I'm not going to write this out in maple form because, you know what, should I? Nah. Okay, and then ys is just minus 174 over s squared plus 6 squared plus s over s squared plus 4. So if you put this into Mobius with the right syntax, oh, another shot of dopamine, guys. Oh, at this point, you're probably going to be like, guys, I'm going to do so well in the exam. there's like 4 green lights so far. I will be fine. Is that true though? So now you have to find, the question is asking you to find, so now you have to do the inverse of Laplace transform of xs and ys, and then enter an expression for xt and yt. So I'm not going to go through, I'm not going to like break it out. I'm just going to show you guys. So L minus 1 xs equals to, well, we have this. So what we can do is, Laplace inverse of 174 over s squared plus 4 squared, s squared plus 6 squared, plus the Laplace inverse of 4 squared over s squared plus 4 squared. Right? Because 16 is 4 squared. So we're going to take this out, the 174. And wait a minute, doesn't and then what does this look like? This look like sine, right? But then we have 4 squared instead of 4. So what we're going to do is it's going to be plus 4 sine 4t, right? Okay. So now what we're going to do this in here, we're going to do partial fractions, right? So the partial fraction is going to be like, so the partial fraction is going to give you like 1 over 20 for like the first one, sorry, minus 1 over 20 for s squared plus 6 and 1 over 20 for s squared plus 4 squared. So I'm just going to take the 1 over 20 out, and you do minus s squared plus 6 squared plus s over s squared plus 4 squared. Okay, what does this look sorry, what does this look like? The cos. Good job. So 174 over 20. So this is minus, so minus cos 6t, or omega squared, 6 squared, so omega 6, plus 174. I'm sorry if I'm coughing into the mic. I'm sorry if it's like the live stream, you guys are like, oh, my ears. I'm so sorry. Cos 4t plus 4 sine 4t. That will be xt. So now we have one more, ys. So let's find the Laplace inverse of, so I'm just gonna, from here I'm just gonna straight away take out the 174. 1 over s squared plus 4 squared, s squared plus 6 squared, and then we have the Laplace inverse of s over s squared plus 4 squared. Okay, so what does this look like? Good job. So this is going to be cos 4t. And then, so this is the same as that. So it's just going to be minus 174 over 20, Laplace inverse of minus 1 s squared plus 6 squared plus 1 over s squared plus 4 squared. So yeah, this looks like the sine, but we have to multiply that in. Feel free to do that in your own time as you're doing this. But basically, the answer would, so minus 174 over 20, and then we gotta multiply like 6 over 6. Wait. So it's gonna be 6 sine 6t. Yeah, because, yep, and then, sorry, it's plus. Yeah, negative is plus, guys. So guys, this is a really good example on why you should make sure you check your workings correct, because you might miss a negative sign. You know, this is a very good example on why you should be very careful and not miss your negative signs. Minus 174 over 20 times 4, 1 over sine 4t, and then plus cos 4t. And that is it. You have solved a whole exam question, and you will be okay. Look at that. We solved it. And that is it. I will now pass the mic to Otto, where he'll talk about Fourier series.
Thank you, Rosh. Okay, I'm not gonna sit on your computer, so don't worry about that. Alright. Okay. Let me just scroll back to that on my device. I'll give it a minute. So, as I was saying, Laplace transform, am I right? Okay, so, guys, we touched on this just a little bit yesterday with our first seminar. Fourier series is applied a lot when you look at partial differential equations, but we're going to be looking at it in a little bit more of a pure sense right now. So, who's ready for some Fourier series? Yeah? Okay! Love that energy. Okay, so Fourier series, we're dealing with periodic scenarios and essentially just transforming any manner of function that is periodic into the, I guess, linear combination of a number of sinusoids, right? And as you use like an infinite number of these, you can find pretty much everything. So, you can note, important for partial differential equations, it's like the opposite of a spoiler. We did that like yesterday, just because we thought that we would rearrange the slides for you this time, but here we go. Okay, so fundamentals. We're going to consider L as like half a period. So a 2L periodic function has a Fourier series as described here. We can determine the coefficients of this Fourier series. Sorry, I was scratching the mic. As described by these integrals, okay? And there's a bit of math behind it, but we're not going to really touch it as to why it works. All you need to know is that sinusoids are funny and integrals reveal coefficients. So let's dive straight into the questions here. First up, we have letting ft be 3 minus 2t squared from just the standard interval from minus 4 to 4. Given that it is periodic, in other words, given that ft equals ft plus 8, we're going to determine, if this function is even or odd, and determine the Fourier series coefficients. Alright, so first up, even or odd? Well, just a transformation of our elementary functions. We know that t squared gives us a parabola. We take minus 2t squared, we get a steeper negative parabola. We add 3 to it, and now it's above the x-axis. It's still even. It's preserved. We love it. Okay. Next up, coefficients. Coefficients, once again, we just head over to our formula sheet. Actually, no, we don't really need a formula sheet for this, right? We can recognize that a0 is just like the average value of our function over the period. An is like, tack a cosine on that to find the coefficient of the cosine. And then bn similar for your sine. Okay? Same. So, to do this, first we find the average. I use 1 on t because I'm an electrical engineer. Cry about it. T is 2L. Okay, so we have the exact same equation here. 2L is t, so same, we find the average. 1 on 8 integral minus 4 to 4 of 3 minus 2t squared dt. We get minus 23 on 3. Too easy. Any questions so far? All good. Fantastic. So, part 2. Part 2, the exact same question. We're now going to find AK. Now note that previously, we just mentioned that this is an even periodic function. What this implies is that the coefficient of our sinusoidal components, our Bn, are all just going to be 0. Because you can imagine a sinusoid is given by like this kind of jazz, where you have 0 centered here. Sinusoids are odd. We want an even function, so we're not going to use the sinusoids. Simple as. Okay, so where was I? Yes. Okay, so now this brings us to my second trick. Essentially, because we're analyzing an even function, we can apply another kind of transformation to this integral that we are, observing. We don't need to take the integral from 0 to 4, from minus 4 to 4. We can take it from 0 to 4 because it is even. Therefore, total area is equal to 2 times one side. Simple enough. All right. And so we just perform this integral. Using integration by parts, the hefty thing it is, we can derive some standard right here, and then just sub in our values. We have A is going to be k pi on 4, and so, quite intuitively, because we're going from 0 to 4, our sinusoidal components both go to 0, and we're left with our cosine value. Now remember, cos k pi, as we discussed, I think yesterday, is just standing in for minus 1 to the k. We're going to talk about that some other time, but essentially, you know that cosine of pi equals minus 1, cosine of 2 pi equals 1, and it just keeps on flipping round and round. Okay, so we have our coefficient AK. Fantastic. Part B. Mind you, these questions are coming from the 2023 Term 1 Question 9 content, so that they are still exceedingly relevant for you guys. Now, we're going to try and determine the greatest negative value of t, given this Fourier series that we've just calculated, to obtain this manner of equality. Alright, so let's do it. Something that we can notice pretty much immediately, right, is on this left-hand side, we want a minus 1 to the k plus 1 on k squared. We already have the k squared given right here, and we have the minus 1 to the k. To get it to minus 1 to the k plus 1, we can just sneak out this negative here and chuck it up in the exponent. So, we do so. Another thing to note is that since we're simply interpreting the entire, Fourier series equaling our function at a point, we know that we can get rid of our constant term, bring it to the right-hand side over here. To give us 3213, we reinterpret this just to make it a little bit nicer. And we're going to drag over our pi squared and our 128. Seems simple as. We go ahead, do so, it's over here, we go ahead and redistribute it, and we arrive at something that's similar to our left-hand side that's desired, and then something that is exactly our right-hand side plus some schmuck, right? So, what do we do given this? Well, let us just consider, why is this bozo sitting in our equation. Okay? What's he doing there? He's contributing nothing. Okay? Because we just want to get rid of him. You can see almost intuitively that if we pick any value of t that is like not 0 for this equation right now, you're not going to have your left-hand side work properly, right? A little bit of massaging it about, you find that that's the only value within like one period that this works. So we say, okay, t equals 0, too easy. But notice that the question has specifics, negative values. 0 is not negative nor positive. It is non-negative and non-positive. So it exists within certain sets, but we don't like it being 0. So because we're dealing with Fourier series and we're dealing with a periodic function, don't let this little minus t squared pi squared on 64 fool you, because that is only like a relative value depending on where you are inside a period. Yeah, we can still rotate this for every 8, right? Because 8 is our period. So we can chuck a t to the, t equals minus 8 to solve this. Sound good? Yes? Okay, nice. So we're now going to look at the second part of the question. The second part of the question wants us to, obtain the result of a famous identity, right? The sum of reciprocal squares is equal to pi squared on 6. How do we do this? Well, first, step by step, let us consider two new sets, okay? Two new sequences, sums of sequences. We can recognize that these two sequences provide us with both what we want and something that we know. And given this fact, we can say that applying simultaneous equations, this first sequence is going to be a third of the second sequence. Okay, that allows us to say that, we don't really need that info. We just construct that 4 times x is equal to what we want, and we know that what we have is 2 times x. And so we double it, which is exactly what we need. It's like kind of intuitive. There's not much more to this question. Okay, so we're just going to push forwards. Periodic extensions, you would have seen me perform one of these yesterday in the first seminar. We can use them in a number of ways, but essentially it's whether it is up to our choice to make our function even or odd. Simple as it's whether we take some manner of function and we're gonna make it odd through a reflection through the origin. We describe it in different ways, so it can be a little bit confusing in some senses. But it's really just saying, okay, I have half of my function. It can be whatever I want. And in fact, I'm going to copy paste this to show us 2 examples. All right. So if we want it to be even, simple as it is reflected. If we want it to be odd, it's a different manner of reflection. Yeah. All right. Let's get moving on. That's a quick bit of theory, and it's also known as the half-range expansion. Okay. So you can also use these to kind of intuit out what coefficients that we're going to be dealing with. If we have an even function, we know that we're not going to be using any sinusoidal components. It'll only be cosines. If we're dealing with an odd one, we only have sinusoidal components, no cosines, right? Fairly intuitive. It also, sometimes, I will just mention, you can alter your function slightly to make it easier, right? What I imply by this is, let's say we have the function given by this, right? And it's periodic around those two states, right? Around these two, the boundary of this area, okay? Within here, it is extended periodically. We don't immediately see anything special about this function. We're going to need to find all the coefficients. But we can make it simpler. When we determine the average value, our A0, it gives us a line. And if we then reconstruct this manner of function about that line, we'll see that this is actually an odd function. And given that it is an odd function in that manner of reconstruction, we can determine the coefficients as an odd function, meaning that we don't need to do half of our calculations for all of our cosines, which are our even functions. Anyways, so let's get moving. And yeah, straight into a question. This is from 2017, a little bit further away, but it is still relevant. We're going to now sketch the odd periodic extensions of f for this period, right? So f is a function given by x on 2 for this interval 0 to pi, okay? And so let's do this. Let's begin with just x on 2, okay? X on 2 extends like this. We'll say from 0 to pi. And now we want the odd periodic extension. Our function here is given as a half period, so this is from 0 to L. L is pi. So we have a repetition about minus pi to pi. Given it is odd, we're going to reflect it, and so it remains being x on 2 as our function. And we proceed to make it periodic. Mind the little mess. I can't draw a straight line even if my life depends on it. But I think we get the point. Yeah? Okay. Now, interesting thing right here. We've defined it from 0 to pi. However, pi at that point hasn't been defined. So there's all these open circles. What should we do with them? Well, for the sake of a, Fourier series, it actually doesn't matter because we have a finite number of discontinuities per period. Okay, it's a little bit of extra theory, but essentially our integrals exclude these points because they have like a 0 width in their area. Okay, so that's part 1 done. Now we're going to go ahead and look at part 2. Show that the Fourier series of this function is given by summation from 1 to infinity of -1 to the n plus 1 divided by n sine n x. Okay, so how do we do this? First up, it's an odd function, as we just discussed. That means that our average value given by a0 is going to be 0, and our even components given by an are also going to be 0. So we only look at our odd components given by bn, and so we take the integral of 2 on L from 0 to pi using our function, and the function substitutes into x on 2. 2 on 2 breaks down, and we just have x sine x, integration by parts once again, and we arrive at our solution. Okay, I mean, that's not entirely what we were expecting. It's not very neat. So, once again, we dabble in, okay, well, it looks like this. Cosine rotates here and here between pi's. This is our -1 and 1 on the unit circle. It cycles, and so, rather intuitively, we consider cos n pi is -1 to the n, and therefore, we have -1 to the n over n, -1 to the n plus 1, okay? As desired. Okay, that concludes that question, and we're going to continue moving. There's only like 7 slides to go, and 5 minutes left to the seminar. Let's try and see if we can like speed run this. Okay, so convergence at endpoints. Before I mentioned that if we go up 100 slides, we have all these open circles, okay? These are like limit points at positive sides and negative sides. They're not equal, okay? Now, what does that mean for our Fourier series, which is a continuous function? Well, I won't say continuous function. It's not always continuous. There can be discontinuities, but it's defined at every value, okay? So we scroll back to where we were. We do have convergence at every point, okay? And so what we do is we say that Fourier series gives us the average of both limits for every point. So when we go ahead and take a peek as like a hidden third part of this question, what does the Fourier sine series tell us when x is equal to pi? Well, we take it from the positive and negative sides. We determined that on the positive side, remember, it looks like this. This is pi. This is minus pi. The gradient is x on 2, so the value of this is actually pi on 2 on the function side of it, and minus pi on 2 on that function side of it, and it is periodic. So we actually have this as the other limit point from pi negative, right? So we have the average of pi on 2 and negative pi on 2, which just gives us 0. So for the Fourier series, when we draw it, we would construct it such that, you know, you go here to here, and then at 0, that is where our closed circle goes for this sine series, Fourier sine series. Yeah? Okay, that concludes that question, and we're going to go ahead and take a sneaky peek at Parsifal's identity, because it might be somewhat relevant in like later cases, but it's more of a proof thing, right? So we're going to prove Parsifal's identity in the case of a two periodic function. So 2 periodic implies that the period is 2. Fair enough. So we go from -1 to 1 of a function, and we want it to satisfy that the integral of the function squared equals 2 times the A0 coefficient squared plus the summation of the squares of all the other coefficients. So to prove this, we want to just break it up, okay? And from this breaking up of the question, we can then break it up into a number of infinite sums, right? Because we have f of x is equal to a0 yada yada. We can then say, okay, f of x times this thing, that looks awfully like the way that we determine the coefficient in the first place, through an integral. So we see that we have an and bn, constants can be sorted out, but then we're left with fx, sine nx, and pi x, and then cos n pi x. So it appears that we're just going to have, for each of these integrals, the constant that existed previously multiplied by an integral that makes itself. And so we look at all of these and we arrive at the exact same working as described right now. Okay. Similarly by B, we have our desired outcome. And so that brings Fourier series to an end, and not only that, this seminar. Thank you all for coming, and good luck with your exams. It's on Friday. You guys got this. I'm certain you guys have studied. Barely even needed this, but thank you for your time.